Suffix trees and arrays build a data structure for quickly finding all places where an arbitrary query string Q occurs in S. Suffix trees and arrays are handy data structure for solving string problems elegantly and efficiently. The proper use of suffix trees often speed up string processing algorithms from O n square to linear time. In its simple instantiation, a suffix tree is simply a tree of the n suffixes of an n-character string S. A tree is a tree structure where each edge represents one character and the root represents a null string. Each pass from the root represents a string described by the characters labeling the edges traversed. Every finite set of words define a distinct tree, and two words with common prefixes branch off from each other at the first distinguishing character. Each leaf denotes the end of a string. Trees help test whether a given query string Q is in the set of strings. We traverse the tree from the root along branches defined by the successive characters of Q. If a branch does not exist in the tree, then Q cannot be in the set of strings. Otherwise, we find the query string in Q characters comparisons, regardless of how many other strings are in the tree. Trees are very simple to build, repeatedly insert new strings, and very fast to search, walk down. Also, they can be expensive in terms of memory. Suffix tree use cases. Find all occurrences of Q as a substring of S. Just as with a tree, we can walk from the root to the node and Q associated with Q. Longest substring common to a set of strings. Build a single collapsed suffix tree containing all suffixes of all strings, with each leaf labeled with its original string. In a depth-first search, on this tree we mark each node with the length of its common prefix and the number of distinct strings that are children of it. From this information, the best node can be selected in linear time. Find the longest palindrome in S. A palindrome is a string that reads the same in order of characters if the order of characters is reversed, such as Madame. To find the longest palindrome in the string S, build a single suffix tree containing all suffixes of S and the reversal of S, with each leaf identified by its starting position. A palindrome is defined by any node in this tree that has forward and reversed children from the same position. Implementations. Since linear time suffix trees construction algorithms are non-trivial, I recommend using an existing implementation. But another good option is to use suffix arrays, which do most of what suffix trees do, but are easier to implement. A suffix array is an array that contains all the n suffixes of S in sorted order. Thus, a binary search of this array from string Q suffices to locate the prefix of a suffix that matches Q, permitting an efficient substring search in O logarithm of n string comparisons. With the addition of an index specifying the common prefix length of all bounding suffixes, only logarithm n plus q character comparison needed to be performed on any query, since we can identify the next character positions that must be tested in the binary search. For example, if the lowest range of the search is Kawabanga and the upper search is Cowslip, all keys in between must share the same first three letters. So only the fourth character of any immediate key needs to be tested against Q. In practice, suffix arrays are typically as fast or faster to search than suffix trees. They also use much less memory typically by a factor of 4. Each suffix is represented entirely by its unique string position from 1 to n, and can be read off as needed using a single reference copy of the input string. Some care must be taken to construct suffix array efficiently because there are O(n) square characters in the strings being sorted. One solution is first to build a suffix tree, then perform an in-order traversal to read the strings off in sorted order.